4.3 Translation Theorem. We're going to talk about two different translation theorem in this class. So the first translation theorem says if the Laplace transform of f of t is f of s, and then the a is the real number, then when we have Laplace transform of e to the at times f of t, it's going to be f of s minus a.
Wait a minute, Dr. Kim. We said when we have the Laplace transform of this is 1 over s minus a. Is that right?
Yeah. However, if we have e to the at itself, or there are some other functions as an addition and subtraction, this is true. But when we multiply e to the at to any other time domain f of t, then we'll use this first translation theorem. So let's take a look at this example. Problem 4.3.4, Laplace transform of t to the power of 10 times e to the negative 7t. So when we have this multiplication of the function, we don't want to do this into 1 over s something. What we need to do, e to the power of something is going to be the translating the domain by this power. So what we want to do, we want to do the Laplace transform of the other function. So let's do the Laplace transform of t to the power of 10. That is 10 factorial over s to the power of 10 plus 1. And that is 10 factorial over s to the power of 11. Then what we need to do, we're going to apply just first translation theorem e to the negative 7t. So whenever you see s in the expression, we have only one s here. Instead of s, we're going to change that into s plus 7, which is s minus a. So this Laplace transform of t to the power of 10 times e to the negative 7t now is going to be 10 factorial over s plus 7 to the power of 11. Let's do the Laplace transform of e to the negative 2t times cosine 4t. So what we need to do, we need to do the cosine 4t first. Laplace transform of cosine 4t. Cosine is what? S over s squared plus k squared. So we have s over s squared plus k squared. Now we have s in the numerator and then s in the denominator. We need to replace this s with what? S plus 2 because e to the negative 2t. Therefore, when we do the Laplace transform of e to the negative 2t, cosine 4t, that is s plus 2 square plus 4 square. Next, if you look at the table, we don't have the pair for 1 over s squared plus 2s plus 5. If we have 1 over s squared plus 5, that's the sign. We can fit it into sign. We can make the numerator to square root of 5, s squared plus square root of 5 squared, and then 1 over square root of 5. And that is sine square root of 5t. But we have 2s, so we cannot do that. So in this case, we can factor this out and then 1 over whatever s plus 1 times, just like what we did for the partial fraction expansion. However, if you put the denominator s squared plus 2s plus 5 into your calculator, you are not going to get roots because that's a complex number. B squared minus 4 times a times c, that is 4 minus 20, which is less than 0. So inside of the square root is less than 0. This is the complex number, so we cannot do that. So if that is the case, what we need to do, we need to make the complete square. S squared plus 2s, so half of this guy and then squared, that is the third one, so that we can have this is a complete square. Since we add 1, we subtract 1, and then plus 5, we still have the numerator. And then inverse Laplace transform of s plus 1 squared plus 4, and then numerator equals to 1. Now we can change this into this form, s plus 1 squared plus 2 squared, and that is the form of sine, right? So also, in order to match the k, we're going to multiply 2 at the numerator and 2 at the denominator. But we have s plus 1 complete square. So we need to multiply e to the negative t. So this is the first translation. And then, of course, we have, I'm sorry, this is 1 over 2, 1 over 2 right there. This was the one of the example that I put it in for the partial fraction expansion example. So if you do the partial fraction, then we need to do
a over s plus bs plus c over s squared plus 4s plus 5. And then we multiply them. We have s squared plus 4s plus 5 and as squared plus 4as plus 5a plus bs squared plus cs. Now we need to look at the square term. We have a plus b, that is 0. There is no square term in the numerator. And s to the power of 1 term, s term, we have a 4a plus c, which is negative 2. And the constant term 5a equals 10. From here, a equals to 2. That means b equals to negative 2. C equals 10. 2 over s plus negative 2s plus 10 minus over s squared plus 4s plus 5.
So again, s squared plus 4s plus 5, that's it's not factorable because roots are the complex numbers. So now we need to do the complete square, 2 over s. I'm going to take out negative 2, and then s squared plus 4s plus 4 minus 4 plus 5. This is the complete square. So I add 4, subtract 4. For the numerator, s plus 5 plus 2 squared plus 1 squared. For the numerator, I'm going to write s plus 2 plus 3. Why? Because we need to separate them to fit in sine and cosine.
2 over s minus 2. We have s plus 2 square plus 1 square. And then numerator, I can have s plus 2. And then s plus 2 square plus 1 square. And then numerator, I have 3.
3 is 3 times 1. So now this is 2 over s, which is 2, minus 2 times. The first one is cosine k, which is 1t, times the first translation, s2, s plus 2. So e to the negative 2t, plus 3 times sine t, e to the negative 2t. Problem 4.3.26. So it is a differential equation. Find the solution using Laplace transform. So 1 times the y prime, do the Laplace transform, s y of s minus y of 0 minus y of s equals the right hand side. 1 will be 1 over s, and then t times e to the t. So we need to take the Laplace transform of t first, and that is 1 over s squared, and then e to the positive t. So that's going to be 1 over s minus 1 squared. Now, y0 equals to 0, so this term is going to go away. And then we collect y of s term, s minus 1 times y of s equals 1 over s plus 1 over s minus 1 squared. Now we divide both sides by s minus 1. Y of s equals 1 over s minus 1 plus 1 over s minus 1 cubed.
And we can do the partial fraction for this term. Then a over s plus b over s minus 1. Then the numerator, as minus a plus bs. S terms, a plus b equals to 0. Constant term, negative a equals to 1. A equals to negative 1, b equals to positive 1.
Y of s equals a is negative 1, negative 1 over s plus b is 1 over s minus 1, and then we have 1 over s minus 1 cubed. The first two terms are very straightforward. The third one, we know t squared is going to be 2 over s cubed. We're going to divide both sides by 1 over 2, 1 over 2 t squared. It's going to be 1 over s cubed. Now, if we want to have s minus 1 cubed, then we need to multiply this guy times e to the positive t. Then y of t equals negative 1 over s, which is negative 1, and 1 over s minus 1 is itself plus e to the positive t plus 1 over s minus 1 cubed 1 over 2 t squared to the t. Problem 4.3.28, you're given this expression, and then if we were using the technique that we learned in chapter 3 to show you so many steps we need to go through. So we do y prime, y double prime, we have this many terms, then we ended up getting a as a 1 over 20. So that's how we find yp. So this many steps. So now, if you're just using Laplace transform, much easier. Let's do it. So the double prime s squared y of s minus s y of 0 minus y prime of 0. That's the double prime. Minus 4 times single prime s y of s minus y of 0 plus 4y of s equals, we have t times e term. So what we need to do, let's do the Laplace transform of t cubed, and that is 3 factorial over s3 plus 1, and that is 6 over s to the power of 4. Now, anywhere we see s, we need to change this to s minus 2. We have a 6 over s minus 2 to the power of 4. Now let's collect the capital Y of s terms. Then we have s squared from the first bracket minus 4s from the second one, and the last one is plus 4 equals 6 over s minus 2 to the power of 4. And then the initial conditions, they are all 0. So this is gonna go away, go away, go away. They're all 0. Then y of s equals 6 over s minus 2 to the power of 4, s squared for s plus 4. That is 6 over s minus 2 to the power of 6. This is s minus 2 squared. We have y of s equals 6 over s minus 2, 6. Now we know t5 is going to be 5 factorial over s to the power of 6. 1 over s6, that equals 1 over 5 factorial times t to the 5. And we have s minus 2, 1 over 5 factorial t5 times e to the 2t is s minus 2 to the power of 6. Y of t equals 6 times 1 over 5 factorial times t to the 5 times e to the 2t. That is 6 times 1 over 5 times 4 times 3, 2 times 1, t5 e to the 2t, 6, 6, 1 over 20, t5 e to the 2t. Before we getting into the second translation theorem, I want you to know this unit step functions. So the unit step function is defined as anywhere t is greater than a, we're going to have a 1, and everywhere else it's going to be 0. So when do we use this unit step function? We just want to sort it out all the positive elements of the signal. We simply multiply u of t. So whatever the function we have times u of t, everything less than 0 is going to be 0. Only positive side is going to be 1. And if you want to have all the signal greater than 1, then simply you need to multiply u of t minus 1. Then everywhere greater than 1 is going to be the live signal, and everywhere less than 1 is going to be all dead signal because we're going to multiply that to 0. So that's the unit step function. So the second translation theorem said if we have a unit function we multiply to any, then we need to have e to the negative a times s. Couple of things you need to pay attention in here. First of all, we have t minus a, t minus a. We have to have a matchup with the t function, and we cannot change this unit step function given. Therefore, if you don't have this t minus a in the t function, you need to force that to make it t minus a match up with the unit step function. That's the first thing. And then second, it is negative a and negative a, unlike like we had we switch the sign, but it's not. And with s terms, not t, we have Laplace transform of this. The first term is okay. Second term, we have u t minus 2, and then third, u of t minus 3. So the first one is 2 over s. Good. And second one, when we do Laplace transform of 1, we have that is 1 over s. However, we have u t minus 2, so we need to multiply e to the negative 2s. That's what we did. And the third one, again, 1 over s times e to the negative 3s. This is the second translation theorem, and we have this, the Laplace transform of, we have t minus 1 right there, right? So we have to match up with the t minus. So what I'm going to do, I'm going to write this guy as a 3 times t minus 1. And if we do this, we have 3t minus 3, but we have plus 1 in the original equation. So we need to have plus 4. And this whole thing times u of t minus 1. So now these two equations are the same. What I did, make sure we have t minus 1 and t minus 1. We cannot change t minus 1 in the u function to something else, but we can play with this the function t to make that happen to match up. And that equal Laplace transform of, now what we're gonna do, we're gonna distribute this to here and here. Then 3t minus 1 u of t minus 1 plus 4 u of t minus 1. Laplace transform pair for t is 1 over s squared. So the first one is 3t is 3 over s squared. Now because of u of t minus 1, this whole thing is going to be 3 over s squared times e to the negative s plus the constant 4 is going to be 1 over s, right? So it's going to be 4 over s. And then because of this, e to the negative s.